Okay. Dr. Juan Diego Soler is a scientist at the Italian Institute of Astrophysics, a research institute in Italy with 20 different research facilities that specializes in astronomy and astrophysics. Dr. Soler is based at one of the research institutes in Rome, in Italy. Dr. Soler is interested in the role played by the magnetic field during the formation of structures in the interstellar medium, such as molecular clouds, filaments, or prestellar cores. His work is both observational and theoretical. He uses simulations of magneto-hydrodynamic turbulence to characterize the statistical tools that provide a link between the observations and the physical processes that structure the interstellar medium. Dr. Soler obtained his bachelor's and master's in physics from Universidad de los Andes in Bogotá, Colombia in 2004. He then moved to Canada for a PhD in astronomy and astrophysics at the University of Toronto, where he worked at the balloon-borne astrophysics group that uses balloon-borne telescopes that operate above 35 kilometers and over 995% above the atmosphere. In the frame of his PhD thesis, he participated in the Antarctic campaigns for the blast ball experiment. He has been a postdoctoral researcher at the French Institute of Astrophysics, at the Max Planck Institute for Astronomy in Germany, and he's now a scientist at the Italian Institute for Astrophysics in Italy. Dr. Soler is very engaged in science outreach. He writes science articles for the main Colombian newspaper and recently wrote a book that is very popular in Colombia. This book. So where he explains aspects of astronomy in a historical context at a reach of a wide audience, as well as his own experiences during his expedition to the Antarctica. Juan Diego was my classmate when I was an undergraduate in Colombia, and it is a great honor to have him today in our colloquium. Let's welcome Dr. Soler.
Claudia, thank you very much for this very nice introduction, and thank you all for coming to this colloquium. I'm going to be talking about something that is a part of astrophysics that you don't listen to very often. We're used to listening about these very big objects, black holes and supernova explosions, but you rarely hear about the interstellar medium. So today I'm going to try and tell you stories about that of galaxy, the interstellar medium, and what we were learning about the formation of stars and the dynamics of our neighborhood in the universe. Okay, so first of all, let me introduce you to my collaborators. So this is a big team of people, but particularly Henrik Beuther, that is the PI of the observations in the THOR survey that I'm going to be talking about. Today, Juan Wang did the reduction of the data, although Juan moved on to be a software researcher at SAP in Heidelberg. And the student of the group was Jonas Seid, that had a big role in some of the findings that we're doing today. And then all of these people have made this work possible. But let's begin with the sun. Okay, the sun is the source of most of the energy that we use here on Earth, from oil to solar energy to wind patterns. And this is how the sun looked this morning. Okay, so you can check this at the SOHO website. This is exactly how the sun is looking at the ultraviolet wavelength of 284 Armstrongs. So the sun is mostly hydrogen by mass. Is 75% of the sun is just hydrogen. Around 25% is helium. The rest is what we astronomers call metals. By atoms, by number of atoms, 92% of the atoms of the sun are just hydrogen. And actually 95% of the atoms that make up the human body are also hydrogen. So in the end, when we talk about hydrogen and we talk about the hydrogen gas, we're talking about the history of what made up the sun and in part what made us all up. So I'm going to be telling you stories of the hydrogen. I'm going to be telling you how this hydrogen lives inside of our galaxy, how it changes phases within our galaxy to create the clouds from which stars are born. And you can see that in this diagram. So the hydrogen, most of the hydrogen was created in the Big Bang and is organized in clouds that we call atomic gas. Okay, atomic simply because it's hydrogen mixed with other metals. These clouds are extremely diffuse. We're talking about like 1 particle per cubic centimeters, and it exists in temperatures between 50 and 6,000 Kelvin. We also know that that atomic gas changes phases and becomes molecular, and it can cool effectively, and it can become cool enough to undergo gravitational collapse and form new stars. Those stars, when they die, if they're very massive, they die in spectacular explosions called supernova. To the energy that is delivered by the stars in the form of radiation or in the form of supernova explosions, we call generically feedback. That's what we astronomers call stellar feedback. When the star dies, it releases a large amount of its material back into the interstellar medium. Some of it becomes atomic again, some of it is ionized, and it becomes part of what we call warm ionized medium. These phases all are part of the galaxy. They compose most of the gas in the galaxy. You can see the percentages there. So the story that I'm going to tell you today is mostly in the upper diagram, how that atomic gas becomes molecular and becomes available for star formation. That story is going to lead us to the bottom side of the panel, stellar feedback, because in the end, we're going to learn that that has a big role in regulating the shape of that atomic gas. Okay, so let's start with the beginning. These are the observations that I'm going to be talking about today. This is the emission by atomic hydrogen towards the galactic plane of the Milky Way. You can see there, maybe you can identify a shell, you can identify some wispy clouds, and we can talk for the rest of the hours about the kind of shapes that we're seeing here. But let's talk about the history of those clouds. So we're able to see those clouds thanks to a branch of astronomy, which is called radio astronomy. The father of radio astronomy is, without very little discussion, Colloquium, who in Bell Labs and in his backyard put this antenna. This is an antenna to observe radio frequencies in wavelengths of, or in frequencies of around 20 megahertz. What you see, those wheels are the wheels of Ford T1 that he put there so he could rotate his antenna. You'll see that this doesn't look like a usual telescope, but he's observing radio waves. And he actually made the first detections of radio waves coming from the sky. And one of the brightest sources in the sky, which is the center of the Milky Way. Of course, this granted him the cover page of the New York Times. And then radio astronomy had a big pause of almost 20 years. The only thing that happened during those 20 years in the sense of radio astronomy was made by this person, Groth Reber. And what he did was he made this antenna himself. This was his pet project, and this was his backyard. And during most of the 30s and beginning of the 40s, he devoted to the effort of measuring radio waves. I'm really sorry I left this title in Spanish. I was giving this presentation in a Colombian university before. So radio astronomy had this big pause for the war. And that's pretty much all we heard about that. And then in the middle of the war, if you see the date there, this is very close to the German invasion of the Netherlands. This is in the Leiden, in the Leiden University. These three people, Jan Oort and Marcel Minert. So Jan Oort, you must know, because he's a very famous astronomer. He named, for example, the region in the outskirts of our solar system, what's called as the Oort cloud. He was the first one to measure the rotation of the Milky Way. They got in contact with this student, that is the one sitting there in the bottom center, Henrik van der Holst. And the three of them in the basement of the Leiden University during the bombing of the Netherlands figure out what we call the hyper-fine transition of neutral hydrogen. They discover that when the hydrogen atom in its neutral state changes the spin of the electron. So there's a flip in the spin that produces a transition. It's a forbidden transition. It's very unlikely for this to happen, but there's so much hydrogen in the galaxy or in the universe that most likely we would be able to see this. So they predicted the frequency of this transition and the wavelength. This is 21 centimeters. This is one of the most famous emission lines in astronomy, because in principle, this allowed us to see the atomic hydrogen in the Milky Way. So 21 centimeters is a band that is reserved. You cannot turn on your cell phones at that frequency. You cannot transmit anything because this is a band reserved for astronomy. They predicted that this band was going to be located somewhere. It was going to be observable because it was going to be beyond the frequencies that are reflected by the ionosphere. And we simply had to sit down, produce receivers that were sensitive enough, and observe it. The first observation of the 21 centimeter line by line emission by atomic hydrogen was made in the Harvard University, 1951, 6 years after it was first predicted. Harold Ewan and Edward Purcell made this box antenna. Look at this. This looks more like what we think radio telescopes are, and they observed for the first time the transition. There's no pretty picture about that because I mean it was the first time that the line was detected, so there was no pretty picture there. Then back in the Netherlands, the team at Leiden University found these antennas abandoned in the coast of the Netherlands. These are Würzburg radar antennas, and they were used by the German troops to monitor the coast of Europe to prevent attacks that were coming from England during the Battle of England. So they refurbished these antennas that were originally designed to be radar antennas. They put sensitive receivers in their back ends, and what they did was use them for observing the sky and look for the 21 centimeter line. So just as a reminder, one of the main features in the sky beyond the stars is the Milky Way that looks like this. This is in Vianney in Colombia. This is not far from Bogota, where I am from. And this big kind of Milky Way, as its name describes it, is our galaxy. This is our place in the universe. And with the 21 centimeter line, when they pointed the radio telescopes to that band, this is what they saw. So in the x-axis, you're seeing galactic longitude. So what you're seeing is just moving across this band in the sky. So you're moving up and down in this image. Then in the vertical axis, in the y-axis, you're seeing velocity. So what you're seeing is Doppler effect. You're seeing the Doppler shift of the 21 centimeters line. And you see that the Doppler shift goes up to 100 kilometers per second, and then goes down to minus 100 kilometers per second. That is the Milky Way rotating. You're seeing the rotation of the Milky Way. That is the part of the conference in which I'm going to assume that you guys are saying, oh, wow, because indeed this is pretty cool. We're seeing the gas in our galaxy rotating. Of course, if the gas in the galaxy is rotating, and we know that the galaxy most likely is having circular motions around its center, we can use this Doppler shift of the 21 centimeter mission to produce a face-on view of the Milky Way. Remember, we cannot see the Milky Way from outside of the Milky Way. The only view that we have of the Milky Way is just a plane in the sky. It's just this band. So we imagine it is a disk, but with this Doppler shift, we can make a reconstruction of the face-on Milky Way. This is the Milky Way as we suspect it looks from above, or as we suspect in 1958, okay? There are some features there that people think are spiral arms. This is a source of big tension in astronomy, actually, because when you do the same kind of observations with, for example, massive stars and groups of massive stars, you don't get the same arms. So if you want to see two astronomers fighting, you can ask them if the Milky Way has 2 or 4 arms, and it will be lots of fun. So give them beer because it's going to be a fantastic conversation. What have we learned in the 60 plus years that have passed since this observation? Well, what has improved a lot is the size of our telescopes. So now we have telescopes like this one. This is the 100-meter diameter dish in Effelsberg. This is in the center of Germany, center west of Germany. And you can use it to produce maps like this one. This is a really tiny portion of the Milky Way. You can fit just a few times the moon in this map, but the resolution is really coarse because the line, the 21 centimeter line, requires that you have a very, very, very large telescope to achieve high resolution. Okay, so you can imagine 21 centimeters is almost 8 orders of magnitude higher wavelength than visible light. So if you want to have the same image that you have with your iPhone with a radio telescope, you will need a radio telescope that is almost as big as the Earth. So so it's very tricky. You need very big telescopes in radio astronomy. So how do you get around making a bigger telescope to get more details in those images? Well, you get a bigger dish. And that's, for example, what we did with Arecibo. With Arecibo, we could achieve 4 arc minutes resolution, but still it wasn't enough. And also Arecibo is difficult because you couldn't point it. Now Arecibo is not working. Unfortunately, it was destroyed. So the only way that we had to improve our resolution was using multiple telescopes and the technique called interferometry, in which you mimic a larger dish by combining multiple antennas. So in this case are the 27 antennas that we have in the Jansky VLA. This is in Socorro, New Mexico. And you can put them in a configuration such that you can mimic a dish that is larger, in this case, a dish that is almost 1 kilometer wide. You can also put the antennas more separately, and you get something like this. So you put the antennas more separately, you try to reconstruct that image, and you get the highest resolution map of the atomic hydrogen towards the Milky Way. That is the data in which I worked. And it looks like this. Oh, sorry, there was a pretty movie. Okay, here goes the movie. So this is the Milky Way. So this is as seen in visible light by Gaia, the Gaia satellite of the European Space Agency. If you zoom in into the galaxy, then you start seeing individual stars, and those big dark regions are interstellar dust. And this is the atomic hydrogen. What you're seeing here as we're moving through the image, we're panning over the Milky Way. So we're moving in galactic longitude, and you're seeing different velocity channels. These are the structures that you get when you observe that line with 40 arc seconds resolution. This is the highest resolution map of the Milky Way ever made. So you can see a whole bunch of stuff there. You can see some artifacts because, of course, interferometry has a price, and it's the fact that you have to combine those antennas, and those produce that kind of texture that the map has. Like it looks a little bit like fabric. I can tell you those are the interferometer antennas that are producing those patterns, but you can also see some weird maps. Well, that's a supernova. That's the remnant of a star, a massive star that exploded. You can see all of these filaments, and you can observe this for hours, as I can tell you I have done, and so my workmates. So what do we learn out of this diagram, out of these beautiful images? Well, the first that you can do is just add all of this emission and see what comes out. And this is what we astronomers call an LB diagram. So it's the same thing that I was showing you before. This is just the amount of emission that you have for different positions in galactic longitude. So you're going across the Milky Way, parallel to the Milky Way. And then in the y-axis, you see the velocity, so the Doppler shift. And there you can see that the H1 kind of traces some of the spiral arms, what we think are spiral arm positions. These all come from models based on other tracers, on the emission from massive stars, and in particular, the maser emission from high mass stars. So the high mass stars produce masers, and for those masers, the emission is so intense that we can determine their position by parallax. So we have the distance by parallax, and we have their velocity just by the shift of the maser emission. So you have a way of mapping distance into velocity, and you get the 3D that is so difficult to get in astronomy. So we have that for a few arms, so those candidates, and we have this for the H1 emission. So of course you can play the game that was played in 1958, and you can overlay the position of those arms on top of this arm model. So for example, we learned that the outer arm of the Milky Way is probably further than we thought. The spiral arm, there you can see it in red, beyond that line that is labeled as outer arm. We think that that outer arm is actually beyond where we thought. But that is not the main subject of the talk I'm going to give today. I want to take you back to this. So you saw how much data we have and how much fun is it to just make up shapes out of these observations. So what I did was using a pattern recognition algorithm to identify structures in these maps. If you were going to just observe each one of these images for all of the velocity channels and observe all of the survey, and you take just 1 second in each one of these images, it would take you 8 hours to go over all of our data. So this is not something that we humans can do by hand or by eye in this case. So what we did was just using pattern recognition. So what is it that we were going to recognize? Because you can see that there are plenty of forms there. There's something like a bubble there in the lower right. There's something like blurry clouds like cirrus. There's some others that are more blobby. There's some others that look like sticks. So what we did was just try to identify some characteristics. In this case, and because it was the success story of the characteristic that we chose to select, it was describing the emission as a series of filaments, as a series of sticks. So how do you describe a scalar field, like is the intensity field, as sticks? Well, we use something that is called the Hessian matrix. So the Hessian matrix method is based on the fact when you have a scalar field, like this one that I'm showing you here, you can calculate the curvature of that scalar field. Remember, in this case, the scalar field is intensity of the emission in each velocity channel. You can calculate the Hessian matrix. So remember, the Hessian matrix is the second derivative, the second spatial derivative. And with that matrix, you can calculate the eigenvalues. With a combination of the eigenvalues from the Hessian matrix, you can, with the eigenvalues of the Hessian matrix, you can trace where is the axis of any elongated structures. You can identify saddle points, but you can also identify ridges. It turns out that the second eigenvalue of the Hessian matrix is very good at tracing ridges, okay? And you can also calculate the angle, the orientation of these structures using the Hessian matrix itself. So that is what we did. We took the emission in the THOR survey. Remember, this is atomic hydrogen emission in different velocity channels that are shown here as different colors. And we just calculated their Hessian matrix and the second eigenvalue. So I'm going to flick between these two images. So these are the filaments that we identified. So I'm going to go back and forth, and you can see how you can describe this field as filaments. Okay, I'm going to do this for the rest of the talk until you guys are so tired that you want to go home. No, I'm joking. I'm just going to show you how did we actually select those structures. So of course, we did it for little postage stamps that then we kind of moved in velocity and in position over all of our survey. So we passed from images like the ones that you have in the left to images like the one that you have in the middle, where we're highlighting the filamentary structures. You can see the red filamentary structures. Those are the actual ones that we observed. And you see in gray, like some weird pattern. That is the pattern of the interferometer that we had always to correct for, because we know that our images were not going to be perfect because of the artifacts of interferometry. And then in the right-hand side panel, you can see the orientation of those structures. Okay, that's kind of cute, but I mean, we're not winning anything. We're not reducing the dimensionality of the problem if we just observe these images. So we started doing histograms. So what we observe is that most of the histograms of the orientation angles of these structures indicate that most of these structures in the H1 emission are parallel to the galactic plane. This is cool because if you think of the galactic plane, is an axis of symmetry. If you go in the vertical direction and in the vertical direction, the galactic plane looks like the electric field of an infinite plate. That means that you have an obvious source of anisotropy. You go up and down, you're feeling the gravitational potential of this plane. And if you don't displace yourself too much, it looks actually like an infinite plane. So this is good. This means that gravitational potential is actually setting most of the anisotropy. So we're finding structures that are horizontal. I'm going to tell you, I mean, you invited me for the colloquium, no? So I'm not going to tell you how amazing it is, but I'm also going to tell you what we tried that didn't work. So you know what I tried and didn't work? The length of the filament is a bad thing to measure. It's very hard because it's very hard to connect things together. The people that work, for example, in identification of rivers or identification of roads using satellite images, they know about this problem. It's really hard to connect these filaments. So the length is an ill-defined quantity. It's very hard. And the width, well, most of these structures that you see here, widths are the width of the Gaussian derivative kernel that I use to calculate the gradient and construct the Hessian matrix. So we think we're not resolving all of those structures. So it was hard. So we tried those two, didn't work, but orientation, that was kind of solid. So here's what we saw, for example, for one 2 by 2 degree tile towards the galactic plane. In the upper panel, you see the emission, the amount of light that is coming from the 21 centimeter line at different velocities. And at the bottom, you're seeing the orientation of those filaments. So you're seeing that most of the filaments are actually parallel to the galactic plane, but it's no fun just to show you that for every 2 by 2 degree postage stamp image and velocity channels. We tried to turn this into we tried to reduce the dimensionality of this problem further. So what we did is we took a page from the book of condensed matter, and we turned this problem into a problem of random walk. So if you think of the filaments as the steps in a random walk, if all of the filaments are parallel, then you have a displacement with respect to the center in the complex plane. So you assume you produce a complex number whose norm is the size of the filament, and the angle is the orientation angle of the filament. And if all of the filaments were randomly oriented, well, you would go back to the center. And as always, reality is somewhere in the middle. So you would have some randomness and you would have some preferential orientation. And you don't have to do the maths now, but if you're familiar with the random walk problem, you know that there's ideal estimator of a preferential orientation. It's called the projected Rayleigh statistic. So this is the equivalent of a sigma for a circular distribution. Basically, what you're seeing here now, and the upper panel is still emission, is the amount of light that you get from the 21 centimeter line. In the bottom, what you're seeing is the significance of the relative orientation, either parallel or perpendicular to the galactic plane. So positive means mostly parallel, negative means mostly perpendicular, and the absolute value of that number gives you the significance of that trend. So we see up to 8 sigma significance in the preferential orientation parallel to the galactic plane. So remember, this is just for a 2 by 2 degree tile. This is for a little portion of the galactic plane, but we could do it for all of the galactic plane. And this is what we found. This is the angle. Most of it, this diagram is purple, means that most of those filaments are parallel to the galactic plane, with 2 very clear exceptions, those 2 islands of yellow that you see up there. If you want to be reminded of, this is the emission, this is the angle, and this is the projected Rayleigh statistic. So the significance of mostly parallel is actually really, really high. Most of the filaments in atomic hydrogen are parallel to the galactic plane, except those 2 islands that I'm going to be talking about in a second. Okay, so how does that look in our beautiful pictures? Or it doesn't look like a monolithic sausage. It's not like we see a sausage and that's what is dominating the structure. No, we actually see all orientations, but the dominant orientation is mostly parallel to the galactic plane, and you can see it here. We still have some vertical structures, but most of the structures are horizontal, are parallel to the galactic plane. Why is that interesting? Because we started to find huge structures. We started to find very big structures. My favorite one, and actually the longest that we found, with conservative estimates, this is 1 kiloparsec long structure. So 1 kiloparsec is around 3,000 light years. So this is an object that is mostly parallel to the galactic plane, and you see it, actually, this is in a region where the galactic plane of the galaxy goes up. So this is below the galactic plane, and it's at 17 kiloparsecs from us. So I know this is quite abstract when you're not familiar with galactic plane geography. So we made a movie about that. So this was made by the student Jonas Seid, the student in our group, that he prepared this press release. So this is artist relation of the Milky Way, where we include all of those spiral arm candidates. Remember, those are just candidates of spiral arms. So this is where the Magi filament is on the other side of the galaxy. Again, we're going to zoom in. And that is the filament, if you haven't seen it before, very clearly. And it completes, it's almost 3,000 light years from one side to the other. And it has enough gas to create 100,000 suns. This is a huge object. This is probably one of the largest objects that has been identified in the galaxy. It's probably bound. We know that it's most likely a filament, and the work of Jonas has been confirming that indeed it's on the other side of the galaxy. It's called Magdalena because I'm Colombian. Magdalena is the main river of Colombia. So I call it in honor of the river that probably made my country exist. And of course, it's very difficult to pronounce. So now they call it Magi, but we all love Magi. And we have some theories for form. The most likely theory is that it was created by shear in the outer galaxy. So this is a numerical simulation by my collaborator, Rowan Smith. So what she does is she simulates a galactic plane. Of course, it takes everything that is in the middle, because towards the middle, we have weird dynamics and we have a bar, and we can talk about that later. But if you let this evolve, this is a hydrodynamic simulation. This doesn't have magnetic field yet. It was made with the Arepo code, which is like the Ferrari of codes at the moment for hydrodynamic simulations and magnetohydrodynamic. I see that in the outer galaxy, you create a lot of these very long structures just by shear. The difference in radial velocity between 2 points in the galaxy is really high. So when you have a little bit of overdensity, that overdensity can be stretched really long and parallel to the spiral arms, even when you don't have a spiral arm model. So we think that that is what is happening. Most likely Magi was created by shear. But Magi is very weird because it's also below the galactic plane. So the executive summary is, we don't really know how Magi formed. It's very difficult to explain how it formed. It could be it could be an interaction with another galaxy. I have a question here in the chat, and is, can you see the bar of the galaxy in 21 centimeters radiation? The answer is yes, we can. But it was not as clearly identifiable as with dust, as was seen in emission from stars with Gaia. Gaia really nailed the bar, but I can show you that in a second. So I'm going to go into that. Wait a second, I have to learn how to remove the chat. Okay, now I removed the chat. Yes, you can see the bar of the Milky Way in H1. So let's go back to this diagram. Now I populated with everything that we know. Pretty much we threw everything we had at this problem. So there, green are star forming regions that we have identifying in other tracers. And the good news is that the most massive star forming regions in this part of the Milky Way are not producing the vertical filaments. So this is not caused by stars in their main sequence. This is not caused by stars that are clustered and are producing UV radiation at this moment. Most likely that is not the case. However, what we saw was a clustering of those vertical filaments towards A and B. C is a local feature. This is called the Rager-Crusher cloud. This is at 100 parsecs from us. This is like our neighborhood. We don't care about that one. A and B is what is interesting because we have lots of indications that is related to star formation. You see how there's like a big cluster of those green stars. Those green stars are regions of star formation. However, it doesn't imply that regions of star formation produce vertical filaments, because you can see a lot of red in places where you have green stars. Basically, we didn't know what was going on. So we tried this with other kind of observations. So we went to these observations. This is the H14Pi survey. These are observations over the whole sky, but at a resolution. Remember, THOR was 40 arc seconds. This is like 24 times lower resolution, but they cover the whole sky. So there you can see the rotation of the galaxy. Actually, it's a good qualifier question, no? Like if you have qualifiers there, you can ask the students, what are you seeing here? The most prominent thing is that you see green, purple on the other side. That is the galaxy rotating. That is the rotation of our galaxy. You see these big spurs that we think they're produced by bubbles of supernova remnants. And that biggest blur of orange there in the bottom, that is the large Magdalena cloud. That is a galaxy that is a satellite to our own galaxy. It's a very big and complex system that is most likely interacting with our galaxy. Okay, so how does it look in orientation? Again, this is the LB diagram. For the person that asked the question, where would the bar be? I'm going to try and annotate. Please don't try this at home because I can't see my mouse. The bar is somewhere around here. Yeah. So we think that this is the bar, like, okay, it doesn't make any sense. Sorry, I'm going to just clear this. We can talk about the bar later. Sorry, it was just too tempting to draw on top of my slides. Now I wish I didn't. Yeah, perfect. I'm going to my drawings and I'm going to go back to the talk. Okay, we can talk about the bar at the end. So this is what we found. So you see there's a lot of blue and red, and it's hard to read LB diagrams, although astronomers assume that everyone knows what they're talking about when they show these LB diagrams. But this is a reconstruction of the face-on galaxy. If you could see the galaxy from the top, just based on circular motions. And what I want you to gather from this plot is that most of the blue is in the center, well, it's towards the inner galaxy, what we call the inner galaxy, which is inside of the orbit of the sun around the galactic center, and most of the red is outside. So this is pretty cool because it means that there's some behavior in the inner galaxy that is not being reproduced outside. And actually, when you do a radial profile, which is actually what I should have shown you from the beginning, we see that that projected Rayleigh statistic goes from mostly negative to mostly positive, and then it kind of goes all around. So this is telling you that the structures, the atomic hydrogen filamentary structures, are mostly perpendicular or have no preferred orientation in the inner galaxy, but as you go out, then they start becoming horizontal. So this supports our hypothesis that in the outer galaxy, most likely you're seeing the shear, and in the inner galaxy, something else is going on. There's some dynamic that is changing with galactocentric radius, with distance to the galactic center. Of course, there's that peak around that dotted line. That dotted line is the solar radius. That is the distance from the sun to the galactic center. So most likely that is dominated by local structure. So we left it there because it has its orientation, but most likely it's just local structure. So how does that look? It looks like this. This is the emission towards one of those very horizontal features. So you can see that it really looks like a big snake and like a monolithic object, but there's some deviations and there's like many filaments. It's not that you just see one object as if you were seeing just the edge of a plate. No, you're really seeing a whole variety in emission, and then you see this one. Have you noticed that this one is up and this one is down? That is the warp of the Milky Way. We are seeing that the Milky Way has a warp. So in one side is going up and in the other side is going down. This was already known, but when you look at it in filaments, you see it very resolved. So you can do a face-on map. You can see that it's blue on one side and it's red in the other. When you see it in filaments, it's even more blue in one side, more red in the other. And then we highlight something that is also known, and is that in the side that is blue, that means where it goes down, it goes up again, most likely because of interaction with other galaxies. So this fact, the fact that it goes down and up, that is the warp. So our galaxy is not simply like a disk, it's more like a potato chip. It's like a saddle point. So let's go back to this diagram. So there is something that is happening with galactocentric radius, and is that you reduce the number of stars. As you go outside in the galaxy, you start seeing less and less stars, and the stars that you start seeing less and less are the stars that are more massive. So you also know that something that is clearly changing with galactocentric radius is the amount of energy that you're putting in from stars. One, because less stars, and second, because this is a disk. You have less stars per unit of volume. You need to cover a larger volume when you're in the outer part of the disk. So that led us to try and check what could be the effect in the H1. So we know that the feedback, the stellar feedback, for example, the explosion of supernovas produces bubbles. So that is well known. It's well known since the 80s. We have identified objects like this that not only look like shells, but also they have the profile of shells. Because remember, we can see the line of sight velocity. We can see the expansion of the shell back and forth. We know that these things exist. But we also know that when you have enough of these stars, you can push the H1 in a shell-like configuration. And remember, the galaxy is like a plate, it's like a plane. And most of the stars, most of the potential is in the plane. So that establishes a scale height just by hydrostatic equilibrium, after which you start seeing that there's more diffuse material. So you can have something that is like the popping of a bubble. You inflate your bubble with the supernova explosion. The supernova heats the gas, pushes the neutral gas like a snowplow. If that snowplow gas reaches the scale height, the bubble pops. And what is left is just the walls of the bubble. And we think that is what we're seeing. So if you look towards the inner galaxy, this is how our filaments look like. These are those filaments that we seem to be seeing vertical. Of course, you see the galactic plane, but you also see lots of things that are going up and down. Those have been called by better astronomers than me, worms. Particularly Carl Heiles coined the term worms and chimneys. And he called them worms because they look like worms that are trying to crawl out of the galactic plane. We think that that is what we're seeing. So when you look at this diagram and you plot on top the confirmed supernova bubbles, you can see that indeed you see less supernova bubbles as you go into the outer galaxy. Unfortunately, completeness in these supernova bubbles is very hard to achieve because it depends on kind of the age of the supernova bubble. It also depends on if the bubble is very young, you can see the hot gas. If it's very old, the hot gas has already escaped. So it's very hard, but it's very clear that most of the supernova bubbles happen in the inner galaxy. We also have the numerical models. When you actually do this in a simulation, so this is by my colleague, Philip Girihidis, he's now a collaborator. When you look at what is happening in a simulation of a stratified galactic plane, so I'm going to introduce you to the different panels before I run the movie because it's going to go fast, okay? So in the left-hand side panel, you're going to see density. Then in the right, you're going to see temperature. Then you're going to see column density. Then you're going to see ionized hydrogen, neutral hydrogen, molecular hydrogen, and carbon monoxide, which is the main tracer of molecular gas. So are you ready? Okay, brace yourself because this is going to be bubbly. This is what happens when you start popping supernova in a galactic plane. You start lifting the gas, of course, you make lots of bubbles, but you also produce all of these vertical structures, which is basically the material that is left when the bubble pops, when it reaches a scale height. So we think that this is what is going on in the inner galaxy. When you have more stars, you have more cluster, massive stars that produce these bubbles, and then the bubbles pop. So we think that we're seeing the effect of supernova feedback in the inner galaxy. And as you go into the outer galaxy, you start seeing the galactic potential and the shear. And then you see kind of the galaxy just unraveling in the edges. You don't have any more galactic potential. Beyond, there's very little stars to maintain a stable potential. You're mostly dominated by dark matter and satellite galaxies and other things. This can be seen in this plot. So these are simulations, the ones that I was showing you before. If you only have the galactic potential and rotation, you produce things that are very parallel to the galactic plane. When you have the explosions, you start lifting material very high and very fast. So this doesn't look like our beautiful worms, most likely because we're missing an ingredient in these simulations, and that is the magnetic field. The magnetic field is coupled with the atomic hydrogen through collisions. So when I talk about neutral atomic hydrogen, I'm only talking about something that has an ionization fraction of like 10 to the -4. And it's still that one ionized particle per every 10,000 neutral particles has enough collisional rates that it couples the magnetic field with the neutral medium. And that makes that when you create these H1 filaments, they are coupled to the magnetic field, and the magnetic field helps stabilize them and produces structures that are naturally elongated. You have less fragmentation of those structures. Of course, I'm not saying that this is exactly what is happening, but we know that the ISM is magnetized. So it would be silly not to consider the effect of the magnetic field, and actually it goes in the right direction. It produces elongated structures. So I know I'm running out of time, so I'm going to start wrapping up with this beautiful image. This is another galaxy. Unfortunately, we cannot see our galaxy like this. We'll never be able, well, maybe some days we'll be able to fly over our galaxy like this. In the left-hand side panel, you're seeing the stars. You're seeing visible light of this galaxy, and you see 6946. And in the right-hand side panel, you're seeing the H1 emission. So you can see that the H1 emission goes much beyond the disk of stars. And there's also some holes, not only a hole in the center, of course, that is the active galactic nucleus of this galaxy, but you're also seeing some holes towards the middle. Do you see that it's really flocculent towards the middle? Then the arms are very well defined, but there's some holes in between. Maybe our working hypothesis is that our galaxy is like that. And what we see as vertical filaments are really the walls of holes like this. But we're still working, putting together the models and the observations to test this hypothesis. So this is pretty much my summary. We started with very complicated observations to which we applied a machine vision algorithm to identify a certain characteristic. It turns out that the characteristic that really gave us the insight was the filamentary structures and their orientation. We applied to a family of models, which are these MHD simulations. Of course, we don't have an MHD simulation that can reproduce the galaxy. So these are numerical experiments that tell us what is missing and what is not influencing this thing. As always, of course, everything influences, but we think it's a combination of supernova feedback, magnetic fields, and the rotation of the galaxy that are producing these structures. What are we doing now? We're trying to see if these properties are inherited in the star-forming clouds, which are traced by carbon monoxide. Spoiler alert, no. You don't simply form atomic hydrogen clouds and then they inherit the properties into the molecular hydrogen. No, it's a bit more complicated than that. And it's so complicated that the European Union funded this project, of which I'm part now. This is EcoGal. The principal investigator is Sergio Molinari in Rome. And we're trying to create a self-consistent model of how the gas changes phases across multiple scales, from the galaxy until stars and the planets that form in the disks from which stars are also formed. So this is a very big question to describe star formation and to describe the cycle of life of the gas. And with that, I'll leave you with my conclusions and I'll take questions. Thank you.
Thank you. Okay, thank you very much, especially because it's 9 p.m. in Rome. So, we are going to start with questions here in the audience. Is there any question? Yes, Grant, you will, yeah, if you can come here, thank you. So we have one question, and then we have people in the classroom, and then also on Zoom.
Great.
Hi, thank you very much for the great talk. So my question is, because you have this really high resolution data on the H1 regions, are you able to put better constraints on the Milky Way mass, or like mass in the disk or something? Because right now, I think it's somewhere around like 1.5 times 10 to the 11 solar masses, I think.
Yes, that is a great question. Thank you. So I'm going to show you with a pretty image. And the answer is yes. We do have better constraints of the mass of the Milky Way. And the way that we do it is the way we previously considered the amount of mass in atomic hydrogen was assuming that the hydrogen was optically thin, that we were seeing all of the hydrogen along the line of sight. And that is not true. And we know it through, you see the dots in this image? So you see that there's like lots of wispy stuff, but there are also some dots.
Yeah.
Those dots are galaxies on the other side of the Milky Way. Like there are galaxies that are beyond the Milky Way. And some of those shadows are H2 regions of ionized hydrogen that are within our own Milky Way. When we observe those spectra, we can quantify the optical depth towards those lines of sight. And that's what we did. And we estimated that we're missing around 40% of the mass in atomic hydrogen that we simply couldn't correct before because we didn't have enough resolution to have enough of these dots towards which we measure the absorption spectrum of H1. So yeah, your question is very pertinent. Yeah, we think that we're missing around 40% of the atomic hydrogen. Of course, we only observe a little part of the Milky Way. We observe like 1/8. So if you extrapolate that, that means like your estimate, the 10 to the 11 solar masses, we're off by a factor of 2 at least.
Awesome. Thank you very much.
Thank you.
Okay. Any other question here from the audience? Okay, so let's move on to the questions on Zoom. Anyone with a question? Yes, Paul?
Hi, thank you that was a very fun talk, but I have kind of what might be a basic question for a non-astrophysicist, but you mentioned there being remnants of interferometry in your data, and I was wondering how easy is it to clean that from your data?
It's really hard. It's really hard. So when you do interferometry, effectively you are reconstructing the Fourier transform of an image, but you're not sampling the UV plane. So the plane in Fourier space, you're not sampling it homogeneously. You're sampling it limitedly, and that is a function of the pattern, your antennas, and your number of antennas. So with the VLA, we had our 17 antennas, and they're set in this star-like configuration, and that's the best that we can do. That works pretty well for recovering the extended emission, except when we find a very bright source. When we find a very bright source, that is star kind of pattern, it spreads into the data. So around very bright regions, for example, the H2 regions, that's when the data gets worse. So I'm going to show you how the sausage is made. There, you can see it, that is around those shadows that you see the patterns being more prominent. Maybe I can move on, and like, no, intentionally I showed you the nice images, but yeah, well, you kind of see it in the bottom one. You see in the bottom panel, in the right-hand side, you see a hole, that blue hole, that is an H2 region. And you can see that it produces kind of a star pattern in the gray stuff that is in the middle. So it is really hard. It is really hard to clean that up. There are two ways of doing that. You can either be very smart with your clean algorithm, and we clean our data until we identify those very well through the residuals. So since they have a predictable shape, we can identify them very well, and we know that they don't produce spurious filaments. The other way that you can do it is you get more antennas. Of course, that is very expensive, but actually we're trying to do that. So you actually helped me introduce something, which is in what I'm working now. The future, so forget this is in Spanish, I'm just going to erase it. The next generation of interferometers are going to be this, well, you guys are in North America, so you're going to have the new generation VLA that is going to have like an order of magnitude more antennas. Here in Europe, we're more invested in the square kilometer array. The square kilometer array is going to be a radio interferometer that has sets of antennas in South Africa and in Australia, such that you can use them simultaneously and independently. And when you have so many antennas and the spacings are larger, and also your receivers are more sensitive, you can really beat those artifacts. But for now, and I think for a while, we just have to live with the artifacts that the interferometer do. But still, we can work around that. And certainly, even if with imaging we suffer a bit, we cannot remove that texture. The increase in resolution allow us to see, for example, things like this one. You see that, can you see my mouse? This is a galaxy there. That dot that is a galaxy that is probably behind that shell, and we can reconstruct the column density and correct for like opacity and stuff like that. So what I'm pointing with my mouse is this guy, and you see those guys? We wouldn't be able to see them without the resolution that we achieve with the interferometer. So it's a compromise. Of course, imaging has to be corrected, but it works fine.
All right, cool. Thank you.
Thank you.
Any other question from the attendees on Zoom? Well, if
Just
not,
on that note,
yes, yes.
yeah, sorry to add. Just on that note, people are also working hard in machine learning algorithms to clean images. Before we were using the clean algorithm that is very traditional, and probably you guys have even used it because it's an algorithm to clean signals in general. But many people are doing efforts now to use machine learning to identify this kind of artifacts. So this is an active subject of research.
Yeah, very, very good also for the students. Very, very useful to go to industry.
It's true.
And have a real salary. Okay. So thank you very much, Juan Diego, especially because it's very late in Italy. So thank you very much for having joined us for the colloquium. And thank you everyone for attending. Next week we will have our colloquium in person. So just for everyone to know. Okay, so let's thank the colloquium. Yes, thank you.
Thank you. Goodbye.
Thank you.